Let me just share my screen so that I have some slides to back up what I'm going to present. Are the slides on air?
Yes, we can see the slides.
So as testers and test automators, we're faced with the challenge that we have to test more and more functionality in less and less time. We saw because successful software grows from release to release, so that we have to test it more and more. But paradoxically, we get less time to test more functionality because release cycles are shortening. And I am convinced that we can only overcome this challenge in the long run if we get more effective and efficient at the same time. And this is where my talk comes in, because test intelligence is a name for a bunch of software analyses that mine the data from our development and test process to help us be more effective and efficient, or in other words, to find more bugs in less time. And I want to both present the research background so that and sketch out how these analyses work, and show you examples from practice so that you get a gut feeling on what they are capable of and also what their limitations are. And before I start, I have a question, or I want to ask a favor of you. If you have questions, please interrupt me directly. Put them into chat, and then Larry can interrupt me and ask me the question. And it needs not be a well-articulated question. As you know, testing looks very different from company to company. Test automation looks different from test automation framework to test automation framework or tool. So if I present something that does not resonate with how you experience your testing environment, please bring this to the chat, then we can discuss that. I much prefer if this gets interactive and you take out of the session what you want, than that I get through my slides in the order that I brought them. So with that out of the way, the key idea I want to present is that we need to get transparency into the black box of software testing to see what changed since the last tests we did, which tests can execute which codes, so that we know which tests to run now or to manually perform now. And because it sounds a bit buzzwordy to say that we need to bring transparency into the black box of software testing, I want to start with a non-testing example that all of you know from medicine, namely X-ray pictures, which bring transparency into the black box of our body. This is an X-ray picture of a kneecap, more specifically of my right kneecap, which I unfortunately broke a couple of years ago in an accident. And those bright fat lines here are the wire pieces that hold together the pieces of bone. And the small wiggly lines are the clamps that close the scar. Sorry, I threw my mouse across my machine. Now we're back at the X-ray. So why do I bring this as a testing example? Because obviously, I mean, you don't plan for an accident, you don't plan for the surgery, but 2 weeks after the surgery, I was made to go to the doctor for quality assurance. And what I found very impressive in retrospect is that, to speak in testing terms, the doctor did not retest all. He didn't even ask me how I feel. He didn't take a blood sample. He didn't measure my temperature or blood pressure. Instead, he took this picture to see if the change the surgeon made resulted in what he expected my bones and stuff to look like afterwards. So it was a very specific quality control approach that saved a lot of effort on his part. And I want to take over this metaphor to software testing. And obviously, we don't have X-rays that can work on software because software is not a physical thing. So instead, we have to make do with the data sources that accumulate changes in data during our development and testing process. So on the one hand, so I'm going to talk about 3 data sources today. And the 3 are the version history that contains all the code base, all the code changes, all the branches made by all the developers that have ever contributed to the software. Second, the tickets or issues or change requests or user stories or bugs. They go by different names, but they are descriptions of the unit of work that live in some ticket system, like Jira or Azure DevOps. And the third data source is test coverage or code coverage, which captures which code gets executed during testing. And I use the terms code coverage and test coverage synonymously in this talk. And my agenda today is as follows. I want to highlight 3 questions that we can answer using this data. And the first one is, where were the most bugs in the past? Because often, if there's a systematic problem in our development or test process, we can see it by bugs accumulating in a certain area. And if we learn about this, we can target this problem at its root. The second one is, where are untested changes? Because in long-lived software, most of the changes occur in most of the bugs occur in those areas that were changed since the last release. And the third one, and I think that's especially interesting for you, for those of you that are interested in test automation, is which tests are most valuable right now. Because a lot of our customers or the teams we work with have very many automated tests, and they run many hours or days, or in some cases, if a lot of hardware is involved, even weeks to rerun the entire test suite. And this is a very long time to wait for a test result. So in this question, I want to look into which small subset of tests can we execute now that has the highest likelihood to find new bugs very quickly without waiting for hours, days, or weeks. So before I dive into those questions, some background on me so that you can place where those experiences that I'm going to present come from. I'm a computer scientist. I studied informatics in Munich and did my PhD in software quality analysis. And I brought for your entertainment how I looked back then and when I started my PhD, and then how I looked when I finished my PhD and started the company. And I've been told that it mostly shows that I always got enough food. But the key message I want to send here is that I look at the topic of software quality and test intelligence through 2 lenses. As a researcher, and I'm still working as a postdoc and supervise some doctoral students, as a researcher, I'm interested in what is really relevant to know about tests. Because unfortunately, often we measure what is easy to measure and not what's relevant to know. And in the founder role, I'm interested in impact. Just by stepping on the scales every day, I unfortunately don't lose any weight. And just by running some software analysis that inspects tests or source code, nothing improves. So in the founder role, I'm interested in how these analyses need to look like and how they need to be incorporated into processes to really result in better software. And CQSE is a spin-off from the Technical University Munich. I'm one of the founders. We are 62 right now, and 58 of us are computer scientists, and 23 of the computer scientists hold a PhD in software quality analysis. So the experiences I'm presenting are from our group and not from me alone. Last slide on background. This is a couple of the companies we work for. And the key message I want to send is that even though obviously testing looks different for a COBOL system running in a bank or a Java or C# application that lives in an insurance company or an embedded system driving in a car. But if we take a step back, the challenge that we have to test more and more functionality in less and less time is present across all those companies and organizations. And the approaches I present are independent of a specific programming language or domain or organization type. So enough background. I think most of you know that software is written in code and that changes are documented in tickets. But from my experience, different people understand different things when I say test coverage or code coverage. So before I dive into the analyses, I want to quickly recap what I mean by test coverage so that we are all on the same page. And for that, I like to use an open source project written in Java called Pixelitor as an example system that I use to show test coverage and for the other analyses later on. This is a screenshot of Pixelitor. You can imagine Pixelitor like MS Paint or a very simple version of Photoshop. It allows you to paint images or edit them and has some blurs that allow you to change the image. And this is a piece of code from the Pixelitor written in Java. One single method called create and show GUI. And it's not important that you read the code or understand the code now for the talk. The key message I want to send here is that code coverage measures which code gets executed while tests are run. And there's software called code coverage profilers that fully automatically capture code coverage in the background. And here you see all the lines that have a green background have been executed during the test, and the lines that have a red background have not been executed during the testing. And the typical use case in practice that we see most teams that use test coverage employ is that they capture test coverage of automated unit tests, and then they look at the test coverage to see, does it match the expectations? For example, in this case, here's an if statement, and the body of the if statement, those two lines, 125 and 126, they are red. That means they were not executed by the test. And now as a developer, I can think, do I need a test for that? Maybe I write another test. So to recap, it captures which code gets executed during testing and is usually only employed for automated unit tests. But today, I want to use it for the entire system testing and not only for single methods. And I want to use it for all types of tests, not only automated unit tests, but also end-to-end tests and manual tests. And to give you an impression what the data can tell us, I like to use so-called tree maps as a visualization. And a tree map uses rectangles to visualize software components. And this is a tree map of the package structure of the Pixelitor. So every big rectangle here is a package. And the size of the rectangle corresponds to the length of the component in lines of code. And now I zoom in. The components stay in place, and the smaller rectangles now are files or Java classes. And if we go in even further, the tiny rectangles are methods of the Pixelitor. And it still holds that the bigger a rectangle, the bigger the corresponding method in lines of code. And now I use this visualization to depict test coverage. This is the coverage of the automated tests of the Pixelitor. Gray means it was not covered during testing, and green means it was covered during testing. In other terms, that means if there's a bug in gray code and we run the tests will never go through code that contains the bug, so we cannot find the bug. If there's a bug in green code and we run the tests, we have a chance that the test runs through the bug and notices the bug, but not a guarantee, because just because a test executes code that contains a bug does not necessarily mean we really find the bug. It always depends on what the test really checks for. So I use test coverage for the entire system and also for manual tests or end-to-end tests. And to drive this home, I have an animation here, where on the one hand side, you see a tree map of Pixelitor. And on the other hand side, we will see a manual UI test we do in the Pixelitor. And we start measuring the code coverage when we start up Pixelitor. And the single green rectangle you see here is the start method. And now as I start the Pixelitor, on the left hand, you see the splash screen, and you see the UI loads. And on the right-hand side, you see the code that gets executed while the stuff on the left-hand side happens here. And here we use one of the blurs to test if the blur works. And on the right-hand side, you can see which code was executed. So the key message I want to send here is we can do manual testing, or we can do end-to-end testing with Selenium or Playwright or whatever, and still capture code coverage. And we don't have to change the way we do our tests, because the code coverage profiler works in the background without affecting the way we test the system. So now we've laid the groundwork to talk about the different analyses. And the first analysis I want to go into is so-called history analysis, where I want to look at where the most bugs occurred in the past. And for this analysis, we use all three data sources. On this picture here, you see a tree map from an industrial software system, roughly 1.5 million lines of code. Every rectangle is a file of the source code of that system. And the darker the color blue, the more often this file was changed during a bug fix in the last 3 years. And this is an approximation for how many bugs were in this file in the last 3 years. It's not exactly the same, because sometimes when a developer fixes a bug, they don't only touch the file that contains the bug, but maybe need to do some preparation in another file or find some minor problem that they can rectify during the bug fix. So there's some noise, but all in all, because there's so much data we analyze here, it's a very good approximation. The darker the color blue, the more bugs were fixed here in the past. So what do we see here? The first thing we see is not so interesting, which is the biggest files. The biggest files here are the darkest. And the bigger file, the higher likelihood it can be part of a bug fix. So that's not so interesting. But the second thing that strikes the eye is that here in the middle, there's a big part that's much bluer than the rest, which means it contains a lot more bug fixes than the rest of the code for the same time span. What happens here? And for this system, when we wanted to understand what's happening here, we measured the code coverage of all the automated tests, for the automated unit tests, for the automated Selenium tests, and so on. And this is the picture we got. Now, this is the same tree map, the same files, but color means test coverage now. So the darker the green, the higher the test coverage in that file. And if it's white, there's no automated tests that run through that file. And you notice that there's a big white area in the center where there's some tests, but way less than for the rest of the system. And now, if we put those two tree maps on the same slide, you notice that it's exactly the region that contains the many bugs is the region that has the least automated tests. So when we found this out, we spoke with the team that builds this system. And we learned the following. On the left-hand side here, this is backend code. On the right-hand side here, this is also backend code. And in the center here, this is front-end code, written in JavaScript. The backend code was written in Java. And for some reason, nobody had ever laid the groundwork to make it easy to write automated tests for the front end. For the back end, there was a lot of unit test and automated test framework in place, so that developers would often write automated tests either before they implemented a feature or after they implemented the feature. But when they built a feature, they also built automated tests. But this was not true for the front end, not because the developers were not convinced that automating tests here was a good idea as well, but because the first step to lay the foundation to make it easy to write automated tests was never done and always postponed. And you can easily see that this was a big problem, because all the bugs here are the ones reported from users from production. And when we showed this picture to the team, it became obvious that this is not a sustainable way to do this project in the future. And in the next iterations, they planned the effort to lay the foundation to build better unit tests for the UI. And when we did the same analysis later on, we saw that the coverage had improved a lot, and also that the amount of bugs in that area had gone down compared to the rest of the system. So to summarize this analysis, from the data you have in your version control system, you can compute such information to see, are there hotspots where bugs are much more frequent than in the rest of the system? And in many cases, like in this case, this allows us to see a root cause of a problem in our quality assurance process. And it's a really simple analysis, because all the data you need from the version history is already there. You don't have to collect this before you can start this analysis. So now is a good time for questions regarding history analysis before I go to the next analysis. And I look into the chat. Please take the time to write more questions or comments while I read the first one. Paul Grossman asks, what is the tool to do this comparison? We have a tool called TeamScale, which we use for this, but the individual parts, like for example, selecting the bugs is from Jira. So there's the data you use is not specific to a certain tool. And because I don't want to make a sales pitch for our tool today, but instead talk about the analysis, because that's independent of the tool, I don't want to talk about our tool too much, but I will stick around, or you can contact me afterwards if you want to know more about the tool. Thanks for the question. Are there further questions?
Before you jump, I mean, just besides the tool, I like, I'm looking at the way you scale out, the way you scale it out using your images. My question is, how would somebody looking at that know, that image, how would somebody, now looking at it, understand what it is being portrayed by it?
That's a good question. And the answer is, if you use a tool that produces tree maps, if you move the mouse over one of those boxes, you see exactly which source code is behind that. So okay. On the PowerPoint slide, you don't see this, but every single rectangle here is a piece of the source code. And source code is typically organized in a hierarchy where you have namespaces and sub namespaces and then classes and then methods. And this namespace hierarchy or package structure is still available in the tree map. And then you can see, if you move the mouse across that, which part of the source code are we talking about? Are we in the back end? Are we maybe in authentication? Are we in the business logic? Are we in the UI? And so on.
All right, thanks for that.
Thanks for the question. And Paul, thanks for the nice comment. So I take this as a link to the next part of the talk, and please continue writing questions in the chat. So here we saw that there was a large area where we didn't test the changes prior to shipping. So the next analysis I want to talk about is how we can directly see if there are untested changes before we ship something into production. And why do I think this is interesting? Because many of the teams we work with have less effort or less resources available than they would need to test everything, independent of whether we talk about manual tests or automated tests that need to be written and maintained. And so we are forced to prioritize and would like to focus our testing on those areas that are most prone to errors. And fortunately, there's a whole research field called defect prediction that investigated which parts of a system are most prone to errors, so that we should focus our testing efforts on. And what this research area did was, for 3 decades, measure prior to release properties of software, push them into a machine learning model, and then correlate them with the bugs they found after release. And what this area found out was that for long-lived software system, meaning everything we didn't start in the last month from scratch, for long-lived software system, most bugs are in those areas we changed since the last release. Now, as testing and test automation professionals, we will probably think, why do you need decades of research for that? Because that also is what our gut feeling tells us. But what we were really surprised is how many changes come into production untested, even in structured testing processes and approaches, because software development is so complex and has so many moving parts. So the basic idea of the next analysis is that we extract changes from the version history and superimpose that with coverage information from all our testing to see which changes we did not yet execute. Now, let's do a specific example. This is a business information system from Munich Re, world's largest reinsurance company, and they gave me the clearance to show this. It's written in C#, and at the point of time where I did this analysis, roughly 30 people worked for half a year. And on this tree map, you see the changes they performed to prepare the next release. Gray means the code didn't change since the last release. Orange and red means the code changed or is new. So here we see on the left-hand side, there's not so many changes. On the right-hand side, there's a lot of change in new code. So we would expect to at least test the right side very thoroughly because there's all the modified in new code. So this is one piece of information for test gap analysis. The second piece is test coverage. Same system, same tree map, but now green means covered during testing, and gray means not executed during testing. And again, it's possible to measure test coverage for manual tests, as you remember from my Pixelito slide earlier. So in this picture, we already have the aggregated test coverage of all test phases: automated unit tests, automated end-to-end tests, and manual acceptance tests and explorative tests that were run on the system. So how does it look if we compare that information? Now we see untested changes, and gray means the software did not change. The code was not modified. Independent of whether we tested it or not, this is gray because we know from experience and from research, we can expect way less bugs in those areas. Everything that's colorful here is the new and modified code, and only if it's green did we execute it during testing. Now, how do we interpret that? The green stuff, hard to interpret. We know it was modified, we know it was tested, we don't know if there are any bugs left. Because as you know, testing can never prove that there's no bugs left, we can only show we found bugs. But all the orange and red stuff is very easy to interpret. We cannot have found a single bug in there because we didn't ever test it. And here's tens of thousands of lines of code in every single one of these components, and they slip through testing entirely unexecuted. Here, if you look at those areas. And the key idea of test gap analysis is to allow you a conscious decision if you want to ship like this. We took this picture on the day before the scheduled release. And I mean, in theory, it needs not be a problem that those massive components were not tested, because it could be that they don't need to work at this moment in time. For example, business information systems often have some type of seasonality. For example, some functionality is only needed at the end of the business year, and maybe if your business year ends in March, you don't need that functionality in June. So it could be that it's not problematic if it's broken. However, in this case, this functionality was expected to work. I mean, they built this specifically for the new release, all the red stuff. So the team decided this cannot be shipped like this, and had another testing phase before they went into production. So this perspective on test gap analysis is for the entire system. And the role it's most useful for is the person who's in charge of the entire testing or QA effort. However, from my experience, often I'm interested in a smaller scope of test gaps, namely individual tickets or issues. And if I talk to different teams, an issue has a different name. Sometimes it's called issue, sometimes bug, sometimes user story, sometimes change request. So whenever I say ticket, please translate that into what it's called in your environment. This is a screenshot from our own development. We use our tool TeamScale for the development of TeamScale itself. And we capture test coverage for every single ticket. And if I click on a ticket, I see a small tree map that only shows those parts of the code that were modified during the implementation of that ticket. And in our experience, this makes it easier to prioritize different test gaps, because often if you have such a picture, there's too many test gaps to still close until you have to ship. and then you want to focus on the most important test gaps. And it's easier to prioritize tickets than code, because the ticket is much closer to business risk than code from my experience. And in our process, you are only allowed to merge a ticket or a branch on which you have implemented the ticket into the release version if there's no non-trivial test gaps left. So here I wouldn't be allowed to merge this branch because there's still test gaps in here. Now, taking a step back, I brought another example how different of our customers use this to give you some more gut feeling how this can look in practice. And some of them use it as a big central repository for code coverage to see how different test stages and test types complement each other. For example, in some, maybe they have a lot of unit tests, but not so many acceptance tests, and they want to make sure that certain features were also hit during the acceptance test. And we have one customer, Munich Re, who has been working together with us for 15 years already, before we incorporated the company even, when this idea was still a research prototype. And with them, we analyzed some of their systems before we had test coverage available. And then many years later, when their CIO changed and he wanted to know if it's still worth to invest budget into the tool, Munich Re made an analysis what the positive effect of test gap analysis on their software quality is. And what they found out is that they reduced the number of bugs that go through testing by a factor of 2. So they've before 60% of the bugs that were in the software slipped through testing, and with test gap analysis, only 28% of the bugs that are in the software slip through testing. Now that sounds like a large number, but this is all the bugs you know about years after shipping into production. So not the bugs you encountered during development or testing, but in a retrospective view, when you have all the bug reports from many years of productive use and then see which slipped through testing when. That concludes my second part about test gap analysis. Are there any questions or comments regarding test gap analysis? Then now would be a great time to type them into chat. My third analysis is about which tests to run if you have too many tests to always execute all of them. And the very basic idea is, let's select a small set of the tests that we execute more frequently than the entire test suite. For example, we have a customer that has 80,000 automated end-to-end tests, and they run for 400 hours. And even if they parallelize them in 50 environments, it takes them an entire night to execute them. And then they've only tested one version, but customers often have other versions or older versions of the software still deployed. So it often takes weeks between the point in time where a developer commits a change and breaks something and a failing test case revealing that. And this is very long. If I break something and a test tells me immediately, then I still know what I broke and I can fix this easily. If a test tells me 4 weeks from now that I broke something, then I have forgotten what I did today. And I've done so many things in between that could also be the root cause, that it's way more expensive to find the bug then. So the key idea is, how can we select a very small part of the test that runs very quickly, but still finds most of the bugs that the entire test suite would find? Paul, thanks for the question. Could you give some context by what you mean, how long it takes? Like a test gap analysis typically takes a couple of seconds, so that between getting the data and seeing the test gaps, and the selection algorithms I'm going to talk about also take a couple of seconds. So you don't slow down the testing process by running these analyses. If you meant something else with the question, yes, gap analysis. The basic idea is that we capture all the data in the background so that you don't have to wait for the results of the analysis. And the only factor you have to wait for is the data transport between the different test systems and the test gap analysis engine. And depending on how your test environment is set up, this can take seconds or minutes, or sometimes if the testing happens in a different part of the company where there's firewalls and stuff, maybe you have to wait overnight so that there can be a data transport. But we try to have this as real time as possible. Hermann, how can we discover bugs in configuration files like YML? Test coverage analysis seems not to be capable of finding out what happens. Correct. So this is one of the boundaries of any coverage-based analysis. It won't work on configuration files. There's one exception. There's some research work that monitors file system access. So then you can notice when a software system reads the configuration file. And if you're lucky and it reads the configuration file in the right moment, then you can use that also for the analysis. But this is like a theoretical answer because I'm not aware of any tool in practice that can do that. But one of the PhD students we worked together did this for its PhD thesis. But this is not part of any practical tool I'm aware of. Hermann, thanks for the question. So coming back to test selection. I want to present two approaches to select fast test subsets. And the first one exploits the fact that most test suites are very redundant. And if we squeeze out the redundancy, we can find a small subset that covers most of the code and finds most of the bugs. And I want to go back to the Pixelitor to give you a specific example of what I mean by this. Imagine we start the end-to-end test suite from Pixelitor. And the first test in that suite is called Test Gaussian Blur. Blurs are an important feature of Pixelitor. So there's test cases for the different blurs. And this is all the methods the Gaussian blur covers. The second test in the suite is called motion blur. What I forgot to say is we measured the test case specific coverage for this. So for every single test case, we measured which parts of the code does it execute. That's how we can draw these pictures. And that's also how these algorithms I'm going to present work. So at first, we ran the Gaussian blur, and now we run the motion blur. And all the code that the motion blur tests that was not tested before is green. And everything the motion blur tests that was also tested by the Gaussian blur is blue. And you notice there's some stuff that's specific to the motion blur, but most of the code has already been tested by the Gaussian blur. The third test in the suite is called lens blur. The fourth test is called smart blur. And I mean, you notice it directly. Everyone is called blur, 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 and they test very similar stuff. So if we take a step back, and here you see the 4 tree maps, and to the right is the green areas they tested. You see the first one contributed a lot of coverage, and then there's saturation, and each subsequent tests contributes less coverage that was not previously tested. And empirically, we know through a lot of research that for most of the bugs in here, in the blue area, either all the tests find that or none of the tests find it. So from an efficiency perspective, it would be better to only test one blur and then test something completely different if we only have a little bit of time and want to find most of the bugs. And this is a chart from a real customer project, not from the Pixelitor demo. And it's from a medical software where the tests run 48 hours. And on the right-hand side, you see the 48 hours. And on the vertical axis, you see the test coverage that the entire test suite produces. And what I want to show you is that there's a lot of these plateaus. And they mean that for hours, there's a lot of tests executing, but there's hardly any new software tested. And that's because there's clusters of similar tests, like those blurs. That's something we typically see in practice. And typically those clusters are, all of the clusters are executed one after the other before we start the next cluster. And the first test from the next cluster produces a lot of new coverage and can find a lot of bugs that the previous tests could not find. And then we spend a lot of time in that cluster again. So the key idea of an analysis called Pareto optimization is to reorder those tests in such a way that we very quickly get a lot of coverage. And there's very many different approaches. And the best approach we found that works for us is to always take that test case next, that per second of test execution covers the most untested lines of code. And if we run this on the Pixelitor, we get the following result. Imagine we have this reordered test suite. The first test we run is called test create and modify selection. Because it's the first one, everything it tests is green. The second one is called change view settings. And you see there's some blue code, but most of it is still green. The third one is second layer. The third one is save image. It's not important what it does exactly, but you notice immediately it's not blur, 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 but very different functionality. And if we put those tree maps next to the ones before, you see that in the same amount of time we used to run automated tests, we have way more code covered. And if we come from the Pixelitor example back to this one, if we run this algorithm on this data set, on this test suite, we transform this chart, where it takes 48 hours to reach 100% code coverage, to this chart. And you see that it selects tests in such a way that very quickly we achieve very much code coverage. In other terms, here in 8% of the runtime, we cover 99% of the code that the entire test suite covers. And now I made a bit of a trick, because I spoke about optimizing coverage. But what we're really after is fault finding capability. And all of this only makes sense if coverage is a good approximation of fault finding capability. And to find that out, we did a lot of research. And by we, I mean our master thesis students and PhD students that we supervised. And the key questions we had is, if I take 1% of the time it takes to execute the entire test suite, how many of the bugs do we find if we optimize a test suite like that? If we take 5%, if we take 10%, and so on. And for that, we need a lot of bugs. And we had two sources of bugs. The first one was from open source systems. We crawled through many open source systems through historic versions to find instances where there were automated tests that failed. And then we would see if we also found that those failing unit tests, if we optimized the test suite in this way. And the second instance was mutation testing. So we automatically inserted thousands of bugs into open source systems to see if the optimized test suite would find that. The advantage of using historic bugs from real-world software is that they're very representative because they are bugs from real-world software. The disadvantage is it's very hard to get a lot of data. We analyzed thousands of versions to get like 50 bugs. The advantage of mutation testing is that it's very easy to get a lot of data, and the disadvantage is that it's not so representative. But combining those two approaches, they cancel the weaknesses out. And luckily, we got the same result for both approaches. So we are very positive that it holds for other systems as well. And in 6% of the time it takes to run the entire test suite, we find 80% of the bugs that the entire test suite can find. Or in 11% of the time it takes to run the entire test suite, we can find 90% of the bugs the entire test suite can find just by wringing out redundancy. So the key idea is that you separate your test suite into two different ones. The small one that you execute frequently, and the big one that contains all the tests that you still execute every now and then. And I have one example from a Bavarian customer, the Bayerische Versorgungskammer. I don't really know how that translates, but they build business information systems to compute pensions. And they had a test suite that ran 20 hours. So it would take an entire day to execute. So you would have to wait at least until next day if you broke something. And what we did with them was take 1 hour of time budget, like 5% of the 20 hours, and build the small test suite that fits into this 1 hour. And this gets executed with every build. But the big test suite still gets executed on a separate machine the next day. And this way, we get to speed up how quickly we find bugs, and also notice which bugs slip through and are found the next day, where you still have to wait as long as before. And we found with them, they've been using this for a couple of years now, that in the 5% of the test budget, they find 70% of the bugs that are in the software. And the remaining 30% are found the next day. So that gives them a big speed up, because often they can fix a bug, try again. If they have another bug, fix that, and so on, before, which would have taken several days beforehand. So the last, and there's one way to make this even better. And this is the last analysis I want to present. And the key idea which we add now is that we also look at what changed since the last test execution we did. And now I have an example from our own system. This is roughly 1.5 million lines of code. And because we analyze other software, whenever a programming language evolves, we need to adapt our analysis software. And the changes you see here were implemented when the programming language Java had a new version that contained a construct called closures. It had its own keyword and syntax. So we had to adopt our scanner and our parser and so on. And what I now do is run a time-lapse video of our automated unit tests. We run 30 unit tests per second. All the methods a single unit test execute are depicted in white in one frame, and then they fade to green, so that you see how the tests distribute and where they run. I start this now. I hope it comes through restream. And to me, it feels a bit like a weather radar, where you see the flashlights going down. And you see that there are some areas which are executed by many different unit tests. You see the coverage slowly building up. But the most important point I want to make here is, if something gets tested, it first gets white and then green. But all the orange and red stuff is still orange and red because we didn't execute it during our tests. I stopped the time lapse now. Back at that time, we had 5,000 unit tests, and right now we have 18,000 or something. But of the 5,000 automated tests, only 4 executed changes we made for the ticket. Not 4,000, 4 tests out of 5,000. But only those tests, only those 4 can find a new bug in the modified code. All the other 4,996 cannot find a new bug because they don't execute any of the changes. And the key idea of test impact analysis is not executing tests that don't run through code that was not changed since the last time you ran your tests. So imagine you have all those tests. Every gray-green rectangle is supposed to signify a test here. And in the first step, test impact analysis throws out all the tests that are not impacted by a change. And if we have unit tests, in the sense that our automated tests test a little bit of code, this works very well. However, if we have end-to-end tests And this is a picture from a Selenium UI test we had back then. Now we're doing mostly most of the tests in Playwright. Everything you see here in white is run by a single test. And if I start the execution now, you see that there's a lot of code that gets executed by many of the UI tests because they have to go through the UI stack and back. And if you change a bit of code that gets run through by all the tests, you don't save anything because all those tests are impacted. So the second step, in case there's too many tests left, is to do the same reordering we had for the Pareto optimization earlier. So that you come from such a picture to such a picture where you hopefully have a failing test very early. So how well does this work? We did the same studies here as well. And we found that on average, in 1% of the time it takes to execute all the tests, we find 80% of the bugs. And in 2% of the time it takes to execute all the tests, we find 90% of the bugs. So better than Pareto optimization, where it took us 11% of the time to find 90% of the bugs, but also more effort. And we also have customers that use this analysis to speed up their CI pipeline, even in a very large parameter space. So to sum up, to compare those analyses, I presented two different ways of selecting those tests to run now, because they are likely to quickly find new bugs. Test impact analysis has the higher speed up, but also requires higher effort to set up and run, because we have to compute the affected tests for every single run on the fly. Pareto optimization is not as good, but much easier to set up, and also works if you, for example, can't compute the tests on the fly. For example, because you're on a big acceptance test where you don't have access to the source code of all the changed modules on time. And some of our users employ this as an optimized smoke test before they run manual tests or before they run expensive automated test suites. They run an optimized smoke test to see if the software is good enough to be allowed into the expensive test phase. I'm just reading the question. Sorry, Michael, I don't have the context for the link. If that's a question, please give some more context. By the way, Michael, thanks for doing a great job hosting Eurostar. I really enjoyed my time in Stockholm 2 weeks ago. Let me wrap up because I'm 6 minutes before the end of my time box. I wanted to present to you today that the data repositories we have in our development and test processes have a lot of information that we can use to make our testing more effective and more efficient. On other terms, how we can use it to find more bugs in less time. And in my experience, a good way to regard them is as a toolbox. There are many useful tools, but they must be fit into your processes so that they work smoothly and really tackle the pain points you might have. And I'm really, as you hopefully have noticed, I'm really interested in this area. I've been working in this area for 15 years, and I'm happy to exchange my experience, for example, through a virtual coffee chat. This is the tool we work on. It's free for open source. It's free for research and teaching. For commercial software, it costs licenses because that's our business model. That's how we finance our company and the further additions of TeamScale. But I'm happy to talk over coffee free of charge. I think we have 4 minutes left. I'm just looking into chat, and I'm really happy to answer more questions if there are any, or just have discussions if you want to discuss something. Let me say thanks for your time at this point.
Yeah, and again, thanks for that. Very interested, and I see the good friend Michael, saying I say thank you for mentioning Eurostar. Yeah, well done, and good job, Mike. Good Before we go, I actually have a little question here. in terms of running the analysis and things like that, wouldn't it be better? And just a question out there: wouldn't it be better if the companies and or teams create less tests and also refactor old tests than just building out thousands of tests that some of them that just doesn't have any value after a while?
Yes, I agree. Like typically, if you have 80,000 tests that run for 400 hours, this is not what anybody in the team wants, and also not how you would engineer this now. And typically, you would have what you would want is a test pyramid where you have very many low-level tests that are very fast, and not so many at the higher levels of the pyramid. And I mean, the test pyramid is an old idea, and one of the mental shifts I had to do when I moved from research into practice was not to preach how things should have been done to teams that inherited software and are not responsible for how it looks like. So I learned that if I only preach from the ivory tower that it's all wrong and they should have done this differently 20 years ago, then they say, okay, we know this. We are in this team for 5 years, and this doesn't help us to learn that several team generations ago it should have been done differently. So these analyses can contribute in coping with these situations, even while you re-engineer such a test setup towards a test pyramid that is way faster. Because often, if something like this grew historically over many years, you can't really re-engineer this in a couple of weeks. But it's also a big re-engineering project to build your tests in a way that they are fast enough.
Yeah, and also I think as well the internal team and the test maintainers, they should take some pride in the work. Like I said, they take pride in the work to realize, oh, I wrote that test 10 years ago, and I don't think that should be still within my test set. That should have been gone, because with all the new, with all the new features and advancement, with all the stuff you would use. So I think so. I have a question here, but Paul wants to know how easy it would be to implement, to say, oh, easy would it be to implement?
Excellent question. It depends a bit on the analysis. Let me just go to the overview slide again. This first one, where's the most bugs, takes a couple of hours. You connect the tool, let it analyze the version history, and you see the stream map where were all the bugs in very short time. If you want to know where the test gaps are, this picture, it typically takes a week or two to get the profilers into all the test environments. And this means you need to schedule a month or two of calendar time until everything is in place, especially if it's a complex environment and we need to wait for a lot of permissions to set things up. And the last one takes the longest if we want to know which tests runs through which part of the software, because there we need to measure individual coverage per test case. And this can be very quick, but this can also take long depending on how long the test suite runs. So this is really hard to generalize. But what we typically start with is test gap analysis. And then if we know the system well enough, we can do test impact analysis as well. Thanks for the question.
Yeah, thank you so much. It was very exciting, and for anybody who want to stay in contact with Elmar, you scan the code, you scan the barcode there, and you could also find him on LinkedIn and reach out and have a chat with him. So Elmar, from
Very thanks.
And myself, it's lovely to have you here, and hopefully we'll meet again somewhere.
Thanks. Have a good day.